Hey, Alex, if I do need the breakout rooms, then I think you need to make me host at some point.
I already made you co-host.
Made me co-host, but then I can't make breakout rooms. Thanks.
Can you do like a backup recording?
Yeah, absolutely.
In case the stream, sometimes the stream has a problem.
Yep.
And then one of the TAs will also join, and you should make them co-host in case there's some like moderation to do, like muting or.
Sounds good. You just let me know who that person is and I'll do that.
Yeah.
And go ahead and start recording so I don't forget.
I mean, muting.
That's funny. For a second there, I thought it was your background music. Oh, is Haihan a TF?
What's that?
Is Haihan a TF?
She's a TA, yeah, but it's usually
TA.
one.
Okay, just let me who you want me to make co-host.
Oh yeah, hi Han.
Okay.
And you can also make me co-host.
Okay. Oh, I guess you already are. No, wait a second. Oh, yeah, no, never mind. Okay.
Okay, let's get started. Welcome back, everyone. Today, we have the great pleasure of having a guest lecture. Carolina Nova will be speaking. Carolina has been a PhD student at the University of Utah and graduated just this year before COVID hit, and is now a postdoctoral fellow at Harvard. And she's also been a TA of this course. And Carolina's dissertation was about visualizing multivariate networks. And so she also ran like a half-day workshop about multivariate networks at the WIS conference last year. And so she's probably the most qualified person to speak on this planet about multivariate networks. And hence, I've asked her to give the lecture today. Carolina, please take it away.
Absolutely. Hello, everyone. Well, there goes my whole introduction. So exactly what Alex said. Graduated recently and spent about 4 years thinking and writing about multivariate networks. So we're going to go through my slide deck today, and then somewhere we're going to kind of take a break and do a little bit of an activity, and then we'll create some breakout rooms. This is probably the first class that I've taught that there isn't a single camera on, but I'll just trust that you all are out there and can hear me, and we will get started. Okay. So I'm going to get started. Everyone can see my screen. So as Alex said, the topic of today's lecture is on visualizing multivariate networks. Now, it's a big name for something we actually see every day. There are a lot of real-world applications of multivariate networks, or MVNs, as we call them for short. One of the most common ones is social media networks, where nodes represent people and edges are the connection between them. More academic application of MVNs are biological settings. So in this case, the cells are nodes. The metabolites are nodes, and the edges are, say, for example, reactions that consume or produce these metabolites. Many of you have probably already heard of something called the Internet of Things. That's another kind of graph network where we have attributes, and those can be either people or devices, and the edges are communication between these entities. So if we go back to the kind of more common type of MVN, which are social networks, a lot of things, most people will immediately think about the connections between people, if you're friends, coworkers, relatives, and so forth. But if you kind of zoom into each one of these people in a graph setting, we also know a lot about them. So in this case, we have network setting, we might have their name, attributes about them like their age, what they do for work, in a student setting, their GPA. And so we can kind of use this very simple concept to define what a multivariate network is, which is the combination of the network topology, or the structure of the graph, and what we know about the nodes and edges, or the attributes themselves. If we kind of zoom back out from this one student that we're looking at and look at an entire network, you can quickly see that the topology information combined with the attribute information makes it very hard to visualize everything. It can get very cluttered. And so this brings to one of the main challenges in how do we visualize MVNs. And that is this trade-off between, are we focusing on showing the structure? Are we focusing on showing the attributes? Because how we choose to efficiently encode one can often interfere, get in the way of effectively visualizing the other. So very big picture, that's what MVNs are. And this is one of the main challenges in visualizing them for different applications. So the bulk of the work that I want to talk about today is for the state-of-the-art report that Alex and I and some of our collaborators wrote and published at Euroviz, I believe it was 2 years ago. And for that, what we did was we looked at over 200 papers from 1991 through 2018 that dealt with how to visualize MVNs in a ton of different settings. So we looked at various types of papers. Technique papers are the ones that actually introduced a new way of doing this visualization. Evaluation papers are those that would evaluate whether a certain technique did or didn't do something well. And application papers, as the name implies, are those that talked about how MVNs are used, visualized, and leveraged for analysis in the real world. So this is the state-of-the-art report that came from that work. So this was, this says 2019, but I think we presented it. Now I don't remember if it was summer of 2018 or 2019. And so this is also available, and I'll link to it on the group website. The key contribution of this work was this typology, so organizing like a dictionary of all the different ways that multivariate networks can be visualized. And we're going to go into a little bit of detail on these different sections, but before we dive into visualizing MVNs, I want to talk really quickly about tasks on MVNs. In other words, what are the kinds of analysis that people are doing with these? And maybe something you might be wondering is, so what is the difference between a task on a multivariate network versus a task on a network or a graph? And I'm going to use the term network and graph interchangeably, but what is it about the fact that these networks have attributes that change the types of analysis we do? And as the definition of MVN implies, there's the combination of topology and attributes. So tasks on MVNs rely on both the structure of the network and the attributes of the nodes and edges. Now, this is a very kind of meta definition, or a little bit hard, so I'm going to just give 2 examples to kind of clarify that. So this is a sketch of me when I have very short hair. And this is a network of all the people that I published with during my PhD. So before I actually came to computer science, I used to work with oceanography, physical oceanography. So I have collaborators in like these 2 separate fields. So let's suppose you're looking at this and you want to know how many of my collaborators in this network are from the oceanography field itself. And so in order to answer this, there's 2 things you need to do. First is you need to follow the structure of the network to see what are all the people, who are all the people that are connected to me that I've published with. And then you also need to look at this attribute of this person. Are they in the oceanography field or are they in the computer science field? And so doing this, you would find that only 2 of my collaborators are from my prior life in oceanography. We could make this a little bit more interesting and say, okay, we not only have information on nodes, so in this case, what field people are from, but we also have information on the edges. So number of times people have collaborated. So here I'm encoding the edges are thicker if people have published together more often and thinner otherwise. And so if you're looking at this, you might have a question of who has collaborated a lot amongst themselves. Or for example, if we're looking for, there's a topology feature called the clique, right? So these are people who have a lot of connections amongst themselves. Which clique in this network has the highest number of publications among them? And in order to answer that, I need to now look at the attributes or information on the edges. And so to answer that, we could see that Alex, Niels, and Mark are people who collaborate a lot based on both the structure and the attributes of this network. Another example I'm going to quickly give on how we use MVNs for analysis is a similar structured network where now the nodes are locations or places, and the edges represent the roads that connect these places. And then as far as attributes, we have the speed limit on the road, so that's kind of how fast you can go in each one of them, and we also have business hours for the actual establishments. So let's suppose I'm looking at this network and my analysis task is to say, okay, I'm going to leave my house. I want to pick up some food, go to the bookstore, and get to work. And my question is, what is the fastest way that I can do this? Now, in order for me to answer that, I must take into account what are the roads that connect the places that I want to go to, so the topology, and as well as how fast can I go on each one and when are businesses open, right? So this is a kind of a variant of the traveling salesman problem, but really because we care about the attributes as well is an MVN task. And sorry, so that's the question that I'm answering here, and we need all that information, topology and attribute information to answer it. So if we look at the 3 tasks that I've talked about so far, what they have in common is that they rely on both structural aspects of the network, so the aspects that are highlighted in blue, as well as attributes, so the aspects here that are highlighted in orange. We apply these tasks to different networks and specifically to different structures in the network. So I want to quickly go through the structures that I'm talking about. We may be wondering, or we may need to apply this task to a single node or edge. Find me the person who has a certain attribute. That's the simplest kind of task. Then we might be interested in the neighbors. Okay, so find all the people that are connected to this person that have a given attribute. Paths are a very common graph and also MVN task. So what is the quickest way of getting from this point to this point, considering all of the edges that are in this network? Clusters, so similar to the task that I exemplified there with the prolific co-authors. And lastly, you can have tasks that are on the entire network. What is the average number of publications in this network? Or what is the average speed limit on the roads in this city? And so you can see that different tasks rely on different parts of the network, which means that there will be different visual approaches to allow people to actually perform those tasks. I'm actually going to quickly skip. I think I've kind of beaten the topology versus attribute horse to death here. And I want to make sure that we get to the activity that I had planned for today. So let's jump into, okay, the actual taxonomy and what are the different ways of visualizing. So hopefully it's become kind of clear at this point what a definition of a multivariate network is, what are the kinds of analysis questions, and at least opened up the question of how can we visualize networks or MVNs in order to support analysis of tasks like the ones I've just described. So coming back to the typology that I showed you earlier from our STAR report, we can kind of break it down into into smaller portions. So first we have the actual layout. So these are different ways that you can visualize multivariate networks, and they're very broadly kind of subdivided into node link representations, which are the ones that if you've ever seen a graph representation is likely going to be a node link representation. Tabular layouts, which are not as common, but you may have seen something called an adjacency matrix. So matrix, quilts, and Biofabric. And then we have tree layouts. And so trees are a form or a subset of graphs. And so we also consider them in this taxonomy. And there's 2 types, inner nodes or leaf-centric. Once we have these different layouts, there's also things we can do, or we're calling operations to them. For example, we can put two of them next to each other. Say you have one visualization that's really good for one task and a different visualization that's good for another task. You can juxtapose them together, still call that an MVN visualization, and kind of have that address the MVN tasks that you need to support. And you can juxtapose them, put them right next to each other, put them on top of each other. So these are, generally speaking, operations you can apply to the basic layouts in order to create MVN visualizations. I do want to quickly distinguish between what a view operation and what a layout operation is. So the view operation are the ones where you have a separate view for topology and one for the attributes. So I've kind of mentioned this a few times now, that the key definition of an MVN is this idea that you have structure and you have attributes. And so how you visualize them can also be seen in light of these dimensions. If you have a different view, say a table for attributes and a node link diagram for the structure, these are separate views, and that's a view operation. However, you can also use multiple views for showing the topology or the attributes, in which case that would be a layout operation. And an example that is pretty common, and we've seen a lot of this with the COVID visualizations, for example, are small multiples, right? So every state get its own little line graph, for example, that's a small multiple. So you're showing the topology over and over and over, but for each one, it's a subset of the data, for example. So that is what a layout operation would be. And then the last part of this taxonomy are data operations, which I won't go into too much, but they really have an influence on the visualization. So the idea, as the name implies, is these are things you do to the underlying data. And this can include filtering out data. It could be aggregating data. It could be clustering or computing new attributes. These are all things that you do to the multivariate network itself, the data, and that have an impact on the visualization, but you're not changing the visual encoding decisions themselves. So kind of a summary of what I just said, we have layouts, two operations, view, layout operations, and then data. I'm going to give you a quick demo. We're going to apply these to a very small network so you can kind of see it in action. So first we can pick a layout. So in this case, let's suppose we start with a node link diagram, which is one of the most intuitive and easy layouts. And on that, we choose an attribute to encode some variable. So let's suppose this is, I don't know, number of COVID deaths per circle or something, right? Once we have that layout, we can apply something like a layout operation. And what that does here is the small multiples that I just described before. So let's suppose we now want to see the number of deaths per state. So now we have that same encoding, which is a node link diagram for the structure and color for the attribute, but we're filtering it so that every one of these small multiples shows a different state or a different subset of the data. If we were, for example, to apply a view operation, if you remember what I was saying earlier, the view operation separates structure from attributes. So what that would look like here is we would keep the structure in the node link diagram, but we would separate attributes out to a separate view, in this case, a table. So we're completely changing what the encodings are in order to still show the structure and the attributes. And then lastly, I'm going to apply a data operation. Let's suppose I'm going to filter out one of the circles and its associated attributes. And so what you end up with is a different visualization that uses the same encoding. So like I was saying earlier, it is one where changing the underlying data has an effect on the visualization, but does not change the encodings themselves. Okay, so let's look at other examples that not node link diagrams and kind of walk through the typology. In order to do this, I'm going to give a single social network example, and I'm going to apply all of the layouts to that social network. So let me introduce you to the social network that I'm going to be talking about. We're going to start off with a woman called Abby, and she has a son called John. Abby is dating a man called Tom, who is friends with a man called Mark. Just move this out of the way here so I can see my whole slide. Mark is married to Sue, and Sue is also friends with Tom. And then the last person in this network is Cole, who is a coworker of Tom's and also John's soccer coach. Okay, so here we have our mini social network. We have 6 people, and we can see how they're connected. This is the structure of our graph. And we have, as far as attribute goes, we have people's names, but we also know more about them. So if we look at all of the people in this network, we happen to also have information on their favorite drink and how many times they've had it in the past 3 days. So we have this variety of drinks, port, beer, Coke, and so forth. And the attribute information is for the last 3 days, how many times have they had this? So this is a node attribute that I'm exemplifying here. We also have more information on the edges, or the connections between people. So here we know that Tom, we can look at the connection between Tom and Cole and see that they have been friends. So that in and of itself is an attribute of the edge. And they've been friends for 3 years. So we know 2 things about this connection, or this edge between 2 people. And we have this information for everybody in the network. So these are people, this is our structure, and these are our attributes. Let's walk through the varieties of ways that we can use node link layouts to encode this specific network. There's a distinction here between the 3 node link layouts in our typology, and the distinction is one where the layout is driven by the structure or topology. So it's, as the name implies, called topology driven layout. And then we have 2 flavors of attribute driven layouts, where the attribute defines the positions of the nodes. And I'll go into the examples, but because the topology drives the layout in this first one, the only other channel that's left for encoding attributes is directly on the node. So we call it on node or on edge encoding. So anything that we know, excuse me, about the node or the edge is going to be encoded directly on top of that node or edge drawing. With attributes, we have a little bit more flexibility with the attributes-driven layouts, because we can use them to either facet or position. And I won't go into too much detail here because I'll show you some examples shortly. So we'll start with the on node and on edge encoding. So here we have the same people that I just showed you earlier. These are the nodes in our graph, and we can represent them with, for example, a circle with a little icon on them. And then we show the edges between them as just by drawing these links. So let's talk about how we are going to encode the attributes here. So we can start just by encoding labels on the edges. This is a very common way of encoding something like a text description of what an edge represents. But remember that we also know how long these connections have existed for. And so if you look at now the thickness of the edges, we can encode, similar to my example earlier in this talk, about how we can encode a numeric attribute with edge thickness. That is for edge attributes. If we look at the node specifically, so here let's see how we would encode attributes directly on a node, say for example for Tom. Let's consider that we have a categorical attribute such as their, I don't know, gender or country of origin. So we can easily use color to encode that on the node. We can also use the size itself of the node for a quantitative attribute, such as their age or anything else that you have that you know about them that's quantifiable. Now, of course, this is still very limiting, right? So here you have the ability to encode 2. Let's suppose you know more things about them. You have more quantitative attributes. We can start using these nested encodings, such as bar charts. So here, let's suppose we had 2 quantitative and 1 categorical attribute. We could do 2 bar charts and, for example, a little glyph for the categorical one. Now, as you might imagine, this is not particularly scalable, and we'll see in an example shortly what are the limitations of this, but this is kind of, generally speaking, the ways in which you encode attributes directly in a node. Here we can see in a review of systems biology, of visualizations in systems in biology, Gallenborg and his collaborators looked at how on-node encoding is used in the field of biology. And you can see here there's a range of different levels of detail. We have nodes where just color is used, and then we go all the way up to actually having these little bar charts with error bars and much more complex visualizations encoded in them. As I go through different layouts and show you real world examples of their applications, on the right side, notice that I will include the little glyph for what category this visualization fits into. And it'll be a combination of layout glyphs as well as operation glyphs. So you can start seeing how those operations that I talked about in the beginning, layout operations, view operations, and data operations, look like when they're used with large or just real world data sets. Another really good use of on-node encoding is for these aggregate nodes. So an aggregate node is one that represents, it's kind of like, could also be called a super node. It's pretty much a node that represents more underlying children nodes. So in this case here, we have what used to be a map of the US, now got aggregated into the regions, and every region got put together into kind of one master node. And that way you have a lot of attributes for that node that you want to show, so you can do these summary plots, histograms, tree maps, parallel coordinates plots, and so forth. So this map actually originally came from this one, which was this map about migrations between areas in the US. So So you have a lot of edges, a lot of nodes. Once you kind of create this aggregate version, it's very amenable to encoding directly on the node what the summary is. So here you can see on the right that we have the icon for both aggregating and for direct on node encoding. A few more examples of different types of on-node encoding. You can actually have images. So here we have actual pictures of cells from microscopes, and those were put directly into the graph so biologists could analyze them. And here we have a really good example of on-edge encoding. So all the examples I've given so far have been encoding directly on the node, but here you have one where you have the frequency of a given connection between nodes encoded directly in how that line is drawn itself. And then here we have an example of a bar chart being encoded directly on the edge. Now, these, as you can see, are small graphs. And so a lot of these on-edge encodings very, very, very quickly don't work if you have larger networks because of clutter and overlap. But for small networks, the possibilities are actually quite large. So kind of summarizing what are the good and the bad about on-node encoding, it's good in the sense that it's very easily understood. People will look at this and for the most part don't need a lot to understand what's going on. As I've mentioned a few times, not very scalable. So the moment the graph gets bigger, you don't have a lot of size for the nodes. So the nodes get really small. You don't have too much area to actually encode stuff on there. And you have a lot more edge overlap. So you really don't have a lot of space to encode anything directly on the edges. So overall, when thinking about using on-node encoding, we recommend it for small networks. And also usually only when you have less than 5 attributes on the nodes itself, or if you have a good kind of zoom in, semantic zooming. So as you zoom in and you have more space, you can render those. And as you zoom out and have less space, you don't. Okay, so the second type of node link layout that is very commonly applied to MVNs is attribute-driven faceting. So let's go back to the example of our network. If you recall, every person in that network had a preferred beverage. So these were the 3, Coke, beer, and port. And the key behind the faceting approach is that every unique value of a categorical attribute is given a region in the graph. So here we have a region for Coke, beer, and port. And now once these kind of layers have been established, then you add the nodes into their specific or their correct layer. So Sue and John both like Coke, Mark and Tom beer, and Abby and Cole like port, and then you add the edges. Now notice that the only restricting factor of this approach is that you have these regions. Where you place the nodes inside each region can be defined by force-directed layouts, by another attribute that you put on the x-axis. That's kind of up to you as the visualization designer. So this layout and this layout are both attribute-driven faceting layouts. So one thing that might become clear as you're looking at this is that you have a lot more edge crossings than you would in a topology-driven layout. So this is where you start seeing this trade-off that I mentioned at the very beginning of the talk, which is, okay, so you care more about attributes for your task. So you can use attributes to define the position, but then the structure of the network kind of suffers in the sense that 2 nodes that maybe were neighbors are now stretched apart and at very different edges of your visualization, and that edge is crossing your entire graphic and creating edge crossings that wouldn't exist otherwise. So really it is about balancing what you're trying to do, what are the tasks you want to support, and what visualization approaches that you're going to pick. So this was kind of like our demo of the feature of what faceting looks like. Let's take a look actually at the paper that introduced the technique of faceting under a different name called semantic substrates. So this is a Ben Schneiderman paper. And here what they're looking at is federal judicial cases between 2 years, in this case, 78 and 2005. And then the faceting is done on whether they were resolved in the Supreme Court or in the Circuit Court. So the Supreme Court is the top layer, the Circuit Court is the bottom one, pink and light green. And the size of the node is proportional to how many edges connect to that node. So it gives you a little bit like of a scented clue as to which nodes might have a lot of edges. Now notice here that in our little example that I just showed you with 8 people, it was already pretty cluttered. So if you were to draw all the edges in this network without any kind of interaction, this would be unreadable. And so what the author is here doing, which is something that is very common in this faceting approach, is you need to leverage some kind of filtering. I will only show edges for nodes that you're interested in. So here we're looking at an interaction where the user selected 2 cases of interest that were resolved in the circuit court. And in doing so, it shows, okay, for these 2, these are all the edges in your graph, and this is how they connect. And you can clearly see that of those 2, I'm sorry, I don't think I mentioned that the edges connect cases that cited each other, or that mentioned each other. So you can see that those 2 circuit cases actually cited mostly Supreme Court cases. So here, if you look on the right, you're going to see that the querying and filtering operation is a crucial part of making this visualization approach work for any kind of network that is even remotely medium to large size. So more than, I don't know, 10, 15 nodes, and you start needing these data operations in order to make it usable and actually leverage the strengths of the technique. So here we actually have 3 things at play. We have the faceting, we have the querying, and then as I mentioned, we also have the encoding directly on the node, both with color and with size. So notice that these different approaches are not necessarily mutually exclusive, and that you can leverage different aspects of different approaches to really encode the aspects of the data set that are most relevant to your analysis. So here's another kind of real world example. This is the US Senate co-voting network graph. So any two senators that voted the same on a certain issue are connected. And the color coding here is whether they're Republicans or Democrats. And so here, this same rendering was then done with this faceting by, I forget what was the faceting criteria here. I don't remember exactly what defined what facets they're in, but notice here that the facets are actually laid out in a tree map fashion in order to optimize the space on the screen. So the faceting doesn't have to be like the 2 examples that I've given so far are just boxes on top of each other. You can leverage other kind of optimal visual encoding techniques such as this tree map. Last example of faceting, this is cells and in the membrane and kind of a different layers that they sit inside of your cell, inside of a cell. And that way you can clearly see which are the metabolites or which are the genes that connect to each other given their position. So this is like their physical position in the cell. So faceting is really great for networks that have important categorical or set-like attributes. So the cost of increasing edge crossings by putting things into different facets is worth it if you really care about these different categories and that your analysis is driven by that. Not as scalable with respect to the number of nodes. Also for denser networks, it doesn't work as well. And topology-driven tasks, so things that care about neighborhoods and paths, are much harder to see because you are now placing nodes according to something that isn't the topology, meaning that you can place neighbors very far apart, like I mentioned earlier, which makes it harder to follow paths and things like that. So ultimately, we recommend these for any networks where you can separate nodes into groups easily and where you really care about that separation for your analysis. Okay, last type of node link diagram that I want to talk about is this attribute-driven positioning. And so before I even go specifically into what it is, I want to give an example of it, which is maps. Maps are the quintessential example of attribute-driven positioning. As the name implies, you are placing nodes according to attributes or something that defines them. Cities are nodes, and their latitude and longitude are attributes. So this is a map that actually I saw at the airport in Reykjavik, Iceland. And this shows all of the routes that Iceland Air flies to, right? And so this is a network in the sense that the airports or the cities where those airports live are nodes, and they're placed on the map according to the latitude and longitude of those cities, and the edges represent flights or connections between them. So kind of a trivial example, but I think it's a great way of illustrating the concept of an attribute-driven positioning. A slightly more academic example here is in a paper called Graph Dice, where here you have a scatter plot where the numbers of papers published is the x-axis, and the date that they were first published is on the y-axis. And circles are authors, and if you collaborate on a paper, then you're connected to that author. So this is another one where you can clearly see that the fact that we're placing nodes according to attributes and not the topology creates a lot more edge crossings. So using filtering and using interaction to isolate areas of interest, I only want to see authors that have more than 20 papers and who have been publishing since at least 1984 or something like that, to reduce the amount of visual markings on your actual visualization. This is a two-dimensional example, and then we have a slightly easier to understand, but using the same concept, one-dimensional example called an edge map. So these are philosophers. This is a really interesting paper if you're interested in looking it up, where philosophers are connected either to people they've influenced or people who have been influenced by them. And here they're all arranged one-dimensionally according to their year of birth or death, their year of some sort. So there's one dimension that you kind of organize on the X, and then when you click on a specific philosopher, you can see all of the philosophers in the future and in the past, and so these edges that connect them to the ones that are relevant. And I forget exactly what the size attribute is, but the idea is that they also use on-node encoding to encode something directly on the size and color of these philosophers. I think it might have been the number of edges that they're connected to. So this is one where if we thought that the edge crossings was bad in a two-dimensional scenario, you can imagine that if I were to draw all of the edges in this graph without any interaction, this would be unreadable. So you'll see here the little filtering show up on the right to the icon. This is another example where you absolutely need to engage with data filtering in order for this technique to work. So it is a very kind of query-driven approach where I need to know what is where I might have some hints, what are the philosopher of interest. When I click on them, then you actually display the edges for that philosopher. So the attribute-driven position is a great approach for quantitative attributes. It really isn't very good for looking at the topology, because if you remember with the faceting, we were kind of restricting where on the screen things were, but you still had some control. So if you wanted to optimize for topology a little bit, but with attribute-driven positioning, you just are fixing the points of these nodes according to something that has nothing to do with the structure of the graph, which tends to really hinder any tasks that are related to the topology. So we recommend these for also small and sparse networks, which is kind of, you can see a blanket statement for all of the node link approaches, because that's kind of one of the main drawbacks of that. Where if you care about the relationships between the node attributes, that they have to be super important to the task that you're trying to accomplish, and where topology really is interaction driven and really mostly there for context. Okay, so one thing I've added here, and this is a little bit of a leftover from, as Alex mentioned, we ran this tutorial at Viz, and kind of like, okay, so you're learning about all this theory of what MVNs are and how you can visualize them. You want to go home and you want to actually use some of this. You want to do this in your project for a class. You want to do this for your own kind of research. And so there's this little section that I've added at the end of every kind of major category, which is, okay, what are the tools that are available to you to create these visualizations? And I've created these two personas. One is a very coding intense kind of approach, or that requires more coding. So we're going to call that's Maya. She's a developer, and those are the ones I'm going to suggest if you kind of fit into that category. And then we have Brad, and I called him a graphic designer in the sense that he wants to use more of a Tableau approach, less of a coding approach, more of a GUI interface. So you'll see these icons in the top left, and that'll indicate if it's more of a coding approach or just a GUI interface. So the approach to doing any kind of node link representation, if you are a coder, is to use D3 in JavaScript, which I'm sure is not a surprise at this point in the class. So definitely there's a ton of resources and examples, and you can really easily kind of link representation that will use like a Spring embedded force-directed layout to find the optimal location for the nodes and graphs. Once you start using any kind of constraints, saying, okay, I don't want it to just be force directed, I want it actually to separate out this type of node into this box and so forth, then I recommend Cola.js. It's actually based on D3. It's kind of like an add-on, really cool. So it's pretty much where you set up these rules and saying, okay, make me a force directed node link layout, but make sure that if the attribute of my nodes is X, never let it go above the middle of the screen, for example, or any kind of attribute-driven positioning constraints. So this is very common for creating these biological pathway maps that are, as you can see in some of these examples. So really, really cool library as well. Cytoscape.js. This is a network, a graph visualization library, but also a graph analysis library. So this is one that will actually do a lot of the stats on your network and tell you, for example, what is the node with the highest connectivity, what is and compute metrics on it. So this is kind of a more of a both a visualization and a graph data structure analysis approach to it as well. So this is all JavaScript approaches. If you are an R or a Python coder, there are a few other examples. So gggraph for R is kind of the way to grow. They recently, I'm going to say less than 6 months ago, came out with a newer version of gggraph. So they're just adding more and more. And when I talk about Biofabric later on, which is one of the tabular approaches, which actually hadn't gotten a lot of traction, recently they've added it here, which always helps. The more it's available as a package that people can just download and use, the more people actually become familiar with it. So this is actually really cool. If you're doing visualization in R, gggraph is great. Both R and Python have a Plotly network graph. A little bit limited in terms of what you can use for encoding attributes, but really great for like a first pass. I want to visualize my network, see what it looks like, and I'm very comfortable with R and Python, for example. Another good Python one is called Network X. Oh, and by the way, all these slides are going to be available. So I'm kind of going through them as mentioning them, but definitely don't feel like you have to keep track of all of these. So this is another good one for Python, both in visualizing them, but they also have a lot of like generating random graphs. They're very open into what a node can be. It can be an image, it can be a text, it can be a lot of different things. So this is a really good one that goes beyond just visualizing and goes a little bit into the data generation and processing side. So these are the coding approaches. And then for purely GUI approaches, and there's always going to be less of these than there will be coding, as is natural with any kind of expressiveness versus usability trade-off. Cytoscape has that library that I mentioned earlier, the JS scripting one, but they also have a GUI where you can just say, hey, load my dot file or my whatever graph file, and then kind of just use their interface to visualize the network. So Cytoscape, and then Gephi is the other of the three that I'm going to show you. The second one, another really good open source. Both Cytoscape and Gephi are open source, actually. Load up your graph and visualize it directly on your screen. And this is one actually that is funny because it's an Excel it's called Node Excel. And can any of you see, it actually took me a while when I first got this icon from them, that the circles overlap and the black parts of the circles make the X and the L in the Node Excel title. So I thought it was like, even after someone told me that, I had a really hard time seeing it. So now once you see it, I guess you can't really unsee it, but it's, I think, really poor design. But anyway, so this is actually a way of doing graph visualization in Excel, which I thought was pretty amusing. I've never actually used it. This is just something I found when I was doing the research to finding different ways that you could do this without coding. And so this supports both encoding attributes directly on the nodes. But it's interesting, this is one of the few ways that you can do attribute-driven faceting, where you create cells, and you can see here in this example, and then the edges connect nodes that live inside different cells. So, yep, there you go. Those are your options for node link approaches. Okay, so let's go into the second big category of visualizing graphs, which are tabular layouts, adjacency matrices, quilts, and Biofabric. We'll start with the adjacency matrix. And the way I'm going to do it is I'm going to go from node link to an adjacency matrix, so you can kind of preserve that mental map that hopefully you have of the graph at this point. So here we have our node link representation that we've looked at before. And the key thing here is to realize that every node is represented as a row. And this is true of all of the tabular approaches. Every node is a unique row. And in the case of adjacency matrices, they're also represented as a unique column. And so the way that you represent an edge in an adjacency matrix is it's at the intersection of the row for that source node and the column of the target node. So in this case, you can see that two people are married, and so that edge is filled in there. Now, notice I said source and target. That is only relevant if you have a directed edge, which in this case it's not. So it's not from Sue to Cole. It's actually both ways. And so it also gets encoded with that person's column and the other person's row. So kind of like it's a mirror, right? So if we take the social network that we're using as an example and apply it to our entire graph, this is what it would look like with an adjacency matrix. And now if we just go back a little bit to the concept of, okay, so this is how you encode the structure of the network. How do you encode attributes on the nodes and edges? So we'll start with the edges since we're looking at them. And one easy way of doing it is actually using, for example, the opacity of these cells. So if you recall, the quantitative attribute that we had for these edges was the length of that relationship, how long they've been friends. And in the node length representation, we did that as the thickness of the edges. And in this case, we'll do it as the opacity of the actual edge. So that's for edge attributes. Now, the cool thing about nodes is because of this, the fact that every node is represented as a row, you can easily juxtapose a table. And every node now has as many columns as you can fit on your screen for attributes. So here we have our nodes' names, their favorite beverage, and how many times they've had it in the past 3 days, for example. We can reorder the rows based on any of the attributes. So here, if we were to reorder, that will affect the matrix as well. And so you reorder the attributes and that reorders the rows and the columns in the matrix as well. So here's a real world application of an adjacency matrix. I really like this example. Most of Mart Stefaner's work, and if you're not familiar with it, is very kind of whimsical like this. This is an adjacency matrix showing the ingredients in cereal. So the nodes are ingredients in cereal, and if they co-occur in cereal, like if you find bananas and apricots, then there's an edge between them. And the quantitative attribute that we're looking at is how often does that happen? And the color we're looking at are kind of different categories, nuts, fruits, and so forth. So kind of a super interesting thing to kind of immediately you can kind of see, oh, these happen a lot together, they happen more, they happen less. In this case, we're only looking at edge attributes, but as you can imagine, you could easily juxtapose here a table that had information for each one of these ingredients, nutritional information of some sort, how many times, if I'm allergic to it or not, or whatever. So kind of a cool application of an adjacency matrix there. Here, there is an entire paper there was a paper that looked at, okay, so we're encoding edge attributes in these cells. Is there a perceptually optimum way of showing edge attributes in cells? So they did a user study and they compared these 4 different versions. In this case, they're doing a comparison. So they have matrix A and matrix B. And they want to see how much more was something in matrix A than there was in matrix B in these edge cells. So you'll notice that for each one of these variants, there's 2 colors. And color A is matrix A, and one color is one color for each matrix. And then they did the user study, and I'll give you a second. I mean, I know that it's not going to be super interactive. I'm going to give you like 5 seconds to think about which one of these representations do you think is the most intuitive? If I were to ask you, which is the edge that had the biggest difference between matrix A and matrix B? So look at these 4 visualizations. So let's suppose you're doing the user study. And I want to know, find me the biggest difference between these 2 matrices. And just to yourself, think about which one you would choose. I'll give you 5 seconds and I'll tell you which one the study actually found. So I was a little bit surprised in the answer. And the answer they found was that participants did best with the black and white nested squares, which I think was a little bit surprising. But really interesting because the problems with some of the other ones were that you couldn't really tell where one edge ended, one cell ended and the next one started. So if you have, for example, the bar chart, which is usually a great way of showing comparison, is if the bars are the same size consecutively, it just looks like one solid slab. So they kind of go into all the perceptual reasons why, but just to show that there is research that goes into how to best show multiple attributes for edges in adjacency matrices. Here's another kind of real world application. This is work that actually came out of Alex's lab years ago, what was this? Well, 2017, I guess years ago, on connections between airports. So every node here is an airport. So similar to that kind of visualization I shared earlier with the Reykjavik airport. And the edges are, how many flights are there between these 2 cities? And so you have this kind of edge information, but obviously for every airport, you also know what city it's in, what state it's in, what's the acronym, what the I forget what it's called, you know, the little short name for it. And so you can use a table. In this case, they juxtaposed a table both for rows and for columns to show attributes because those two were not necessarily in the same order. And so the last adjacency matrix example I want to give here is, actually, no, I'm going to give one more after this one, which is this idea that for mirrored matrices, so for undirected graphs, the top right and the bottom left are the same, right? Like I showed you the marriage ones, they're the same. So you can, instead of encoding something twice, what you can do is say, okay, I'm going to encode the edges on the top one, and then I'm going to encode another attribute on the bottom half, for example. So there are smart ways of kind of reusing for undirected graphs that space in your adjacency matrix. So this was a paper whose contribution was kind of focused on that. And then this is something from a poster session from another one of Alex's students that kind of shows an adjacency matrix to show data at different levels of granularity. So kind of this you can really see that nested structure here on the left where you have the US divided by regions. So, excuse me, the dark blue represents separate regions. Then if you go one level in, it's kind of closer and closer until you get all the way down to the state level. So just kind of a different way of looking at graph structures that captures different levels of semantic zooms. One of the key aspects to think about when visualizing adjacency matrices is the concept of matrix reordering. So I want to show you here a quick demo. This is from a matrix representation of all of the characters in the Les Mis movie book thing. And it's really cool to see how as you order them differently, you see completely different structures. So here, it is initially ordered alphabetically by name, but if you go over here and click and say, I now want to order it by frequency, you can see these structures appear. Or you might want to say, I want to order it by the actual clusters in the network, and that will change the representation or the visualization of the matrix as well. And so a key element when you're visualizing things as a matrix is, how does the ordering of my rows and columns reflect the structure of the graph or attributes on the nodes and edges or anything that makes semantic sense for the types of tasks that I'm going to actually be employing? You'll see some user studies run. If you think of past research, there were user studies done on matrices where the ordering was alphabetical, and that's potentially really, it drew a lot of criticism, because if you're ordering things alphabetically and yet asking people to find clusters or topological features, you are not optimizing your visual encoding to perform that task. And so just definitely something to keep in mind when using adjacency matrices. Speaking of reordering, the very common JavaScript library to do that is reorder.js, which was introduced by Jean-Daniel Faquet in his group Enria in France. So definitely, if you're implementing adjacency matrices, check out reorder.js. Overall, adjacency matrices are great for very dense and connected networks because there is never any edge overlap based on the way that they're encoded. They do require a lot of space, right? Because every node will take up a row, and so it can grow very quickly. And like I mentioned, there is always that added complexity of which is the right reordering algorithm for my task, and does it change from task to task, for example. So we recommend that we use adjacency matrices for small, dense networks that have a lot of rich node and or edge attributes, because you have that added space to add in a matrix for, a table of attributes, or to encode them directly inside the edge cells. And it's really good for all of the tasks except for those that involve paths. Following paths in adjacency matrices is particularly challenging because there is no guarantee, actually very rarely happens, that consecutive nodes are placed consecutively in the matrix. So if A is connected to B and then B is connected to C, there's no guarantee that C is next to B, right? It could be all the way over here, and there's no line or a visual trace that connects them. So you need to conceptually go look for C. So it's one of the bigger drawbacks of actually using adjacency matrices. So I'm wondering with timing if I should do my activity now. So this, let me think here. We have Quilt and we have Biofabric. Okay, we will finish up the tabular approaches and then we'll kind of go through and do the activity. Let me think here if I'm going to cover Quilt or if I'm going to go straight to I think I'm going to skip quilts and go into, yeah, I'm going to do that. I'm going to skip quilts. Quilts is a variant of adjacency matrices, so the slides will up here, but just to make sure that we have time, if we have time, I can always come back to it, but I really do want to cover Biofabric. So this is kind of a new-ish technique that is only now gaining traction, and there's a lot of potential both in research, but also in kind of new applications that haven't really been explored. So if we go back to the social network that we were talking about earlier, in the sense that like all tabular approaches, every node is represented by a row. In this case, edges are represented by connecting the rows from the source and the target. So here, if Sue and Cole are connected, that's how you would draw the edge. So if we think of our social network, this is what it would look like in a Biofabric setting. Now, similar to the adjacency matrix, because every node is a row, you can still associate this table of attributes, right? So here you have a column for their name, a column for their beverage, and a column for, I don't know how many beverages they've had in the past day. But the cool thing here is that notice that every edge is also associated to a column. And so the same way that we juxtapose an attribute table for nodes, we can juxtapose an attribute table for edges. So here now we have information on the edges such as the type of the relationship and how many years it's been happening. And that's what it would look like here. Remember, we can still use and leverage other techniques. So let's suppose we wanted to use on-edge encoding. We can now encode, for example, the type. So all of the friend edges are in yellow, but use the table either to distinguish other attributes or to add information. But it's really cool in the sense of thinking, okay, I have this one channel, say color, that's pre-attentive, that's really great to call my viewers' attention. But then once they kind of find, oh, these are my edges of interest, then they can go into this table of attributes to say, oh, now I can look at what other attributes I know about these connections. We could also use, if we use width as another kind of directly on-edge encoding, we could say, okay, now let's encode how long people have been friends directly as a on the edge marking itself. And here you can see that the mother's son for 12 years is the one that kind of really pops out. So this is a cute little small example to show how it works. I want to show you like that Les Mis example that I've shown you in the adjacency matrix. If you were to take that Les Mis example and encode it as Biofabric, it looks like this. So not as easily readable, and that has to be one of the main kind of drawbacks, is this learnability and this getting used to a different encoding. And as you can imagine, also very hard to follow paths with this, but really a lot of potential in terms of the space for showing attributes on nodes and on edges. So the great thing about Biofabric is it can be used to visualize both edge attributes and node attributes. So definitely kind of one of the pluses. Sorry, two thoughts at the same time. The bad thing is it's really not great for topological features like neighbors and clusters. It's actually for any kind of topological features, it's really not great, including paths. What I was going to say was Biofabric was, as the name implies, developed for biological applications. But it works, and this is why we actually put it as just a generic MVN visualization technique, works for any kind of graph that you have attributes on the nodes and edges for. So we recommend it for very small and sparse networks, but particularly those that have a lot of node and edge attributes, right? Because that's one of the strengths here, is that you can kind of expand both vertically and horizontally to include those. Kind of bringing us back to the tools and applications for tabular approaches. So JavaScript, you can do adjacency matrices with D3. You can do anything in D3. So this, and the demo that I showed you was a D3 implementation of it. Also in D3, you can do Biofabric, and actually this implementation also was done directly in D3, so you can find it on the biofabric.org website. The cool thing, remember I was mentioning earlier about the R implementation of gggraph just recently added a library for Biofabric. So you load in your graph, and all you got to do is kind of go new, or I forget exactly what the syntax is, I haven't used R in a while, Biofabric, and you give it that data structure, and it will draw it for you. And so I think it's like a really nice, these libraries provide a really nice balance where they're still scripting, so you still have some control over expressiveness. They'll kind of give you the starting point, and then you can say, okay, now I'm going to encode with color on top of this, or I'm going to add attributes on top of this. Versus D3, as most of you know, I mean, they do have some layouting abilities, but it's very, very expressive, but also requires a little bit more scripting. So as I've gotten to use more R, I've really liked it as well. It has a little bit more of these out of the boxes visualizations, and you can kind of quickly see, okay, is this an appropriate visualization? And then if yes, you can customize it or go ahead and implement it entirely yourself. So adjacency matrices in Biofabric will also technically allow you to build an adjacency matrix, although it's kind of encoded as a little bit of a heat map, so the wording's a little bit different, but it does work. Python is one where it is definitely encoded as a heat map, and so it interprets it as a heat map, which technically is the same thing as a matrix, right? Where you have rows and columns and you have an attribute, a value for that thing in the middle. But obviously you're now limiting yourself to one value, which is this heat value. And so it's not as flexible as, for example, being able to put in a bar chart or a line chart or something in there. So Python is really not the most flexible as far as encoding attributes directly in your adjacency matrices. And then surprisingly, Python actually supports quilts. Quilts is the one that I skipped over in the interest of time. And I say surprisingly because it doesn't support the other ones as well, but quilts was actually originally designed and developed in Python. So it is available there. And then for a GUI only kind of approach, you have Tableau, which also recently implemented the ability to do Biofabric. So this is what I was saying earlier. And like when Biofabric originally came out as this bio-specific application, it kind of lived only in the research world. But over the past, I don't know, I always get these time estimates wrong, but let's say year or so, it's been kind of adopted by these more ready to go, here, just use our library Tableau interface or the R library. And this really is a powerful way of getting people to become familiar with, understand the encoding, and actually use these techniques. So kind of, it was interesting to see the kind of growth of Biofabric into slowly becoming part of the vernacular of visualization designers. So Tableau for Biofabric and for quilts as well. Genea quilts is, so sorry, I skipped over the quilts and I'm still giving you examples, is a downloadable implementation of quilts as applied to genealogies, a little bit outdated though. And then there is the last one, so we have quilt, yes, but there is no GUI interface for adjacency matrices, unfortunately. It's as you know, intuitive or not intuitive, as common as they are, there isn't an absolute no coding approach to them. Okay, so we've gotten to the part where we're going to take a break. I'm going to take a break from talking. You guys are going to take a break from listening to me, and we're going to do a quick activity. This one is, I want you all to navigate to this website, and I'm going to leave it open for a bit here. And this is a little tool that I built for the tutorial, so it's really useful now, which is you put your Twitter handle in, and it's going to give you the people you've been interacting with recently. And I actually have it pulled up here so I can show you as well. This is what it's going to look like. And let me know if I'm going to put it back here real quick so everyone has a chance to kind of follow. It's bit.ly/Twitter-network. This is what you're going to see. So here, I'm going to put in my Twitter handle, and it's going to go in and grab, these are the people that I have recently interacted with on Twitter. So Alex, obviously, the Viz Design Lab, Harvard VCG, my current institution, Hans Peter, my current supervisor, and Michael Barish, I think I might have, I don't know if I liked or something or retweeted. So the kind of edges that you're going to see in this graph are either the type you retweet someone, you mention someone, or you quote someone. And those are the kind of interactions you have. And so this is the graph that you're going to be working with for this activity. And then you get a little table here that shows these are the nodes in your graph. So my code will pretty much grab 5 people, and then all of the interactions between those 5 people. Now, if A, you don't have a Twitter network, a Twitter account, B, you don't like the way it looks, I've created a few sample default ones. So you can say, I want to look at Jeff Harris, Barack Obama's, and so forth. And these are kind of interesting too. And that will kind of update it as well. So what we're going to do is, while you go ahead and do that, I'm going to create the breakout rooms, and we can start the activity. Actually, before I stop sharing my screen, why don't I go ahead and just give the instructions? Actually, all you need for the instructions is this. You're going to pick any of the representations that I've talked about today, and you're going to sketch it out. Piece of paper, iPad, or just kind of, and you're going to sketch out your own. I'm going to put you in groups. So I'm wondering, and Alex, I see that you're back, if we should have everyone do their own, or if we should have one network per group. Kind of.
Usually having a bit of discussion in a group is great.
Yeah, yeah. So let's do that. We'll do groups of, okay, so let me see, how many people do we have? And
do enough groups so that you have 3 or 4 people per group.
Yep, yep. Okay, so we have 48 participants. I'm going to create 12 groups. I'm going to randomly assign them. And then between 3 and 4 people per room. Okay, great. And I guess, Alex, that's not going to randomly assign any of the co-hosts, right? Or if it is, we'll just take them out. Yeah. Yeah. Okay. Create these. Okay, great. Are there any questions before I so the idea is someone shares their screen, goes to the URL. I'm actually going to make sure that I enable screen sharing here. Go to the URL, pick one of the group members' Twitter network or one of the default ones. You're going to see the actual table with the information and that little no-link representation. Don't draw the same no-link representation as you see there. If you're going to do a no-link representation, that's fine. Use an attribute-driven one, encode some attributes with color, I don't really care. And then kind of, as a group, decide how you're going to encode this. Have one person sketch it out and the rest is just conversation. It's going to be about maybe 10, 12 minutes. And then I will bring everyone back and I'm going to ask for some screen sharing for groups to show what they came up with and explain their encodings to the rest of the class. And feel free to just ping us if there are any questions and I will kind of go into the rooms and check on anyone's progress. I see there's a few things in the chat. If there are any questions, oh, thanks for posting that, Sunny, before I open the rooms. Okay, great. I'm going to go ahead and open the rooms and I will see you all shortly. I think I might move. So room 12 is Haihan and just 2 people. Let me see if there's a room with less people that I'm going to move one of them to room 8 and one of them to room 6. Okay, let me just, hey, Michael, you're still here. Michael, can I ask you to, instead of, oh, I wonder if I can change. I don't think you can change rooms, right? Let me see. Michael, I'm going to move you over to room 8. And I'm going to move Leo over to a room with less people. Room 6. Okay, now everyone has, okay, so I see Michael must have stepped away. Okay. So 3:30, Alex, this goes until 4, right? Or right before 4? You're muted. You're muted.
It goes till 1:45, and just FYI, we're still streaming on YouTube.
Yep, yep. Yeah, just wanted to remember. Okay, so I think that'll be good timing to come back, do the activity, and maybe just finish up with the website.
Yep.
Great, thanks.
Yeah.
Okay, I think we have everyone back here. Cool, I see some faces. Okay, so what I want to do is we only have 5 minutes left. So I was hoping to get some volunteers from people who have a sketch they'd like to show. You can share your screen, you can hold it up to the camera. The idea here is really to have a quick discussion on how did you encode, what was your network? How did you choose what to encode? And what do you think your visualization is particularly good or potentially not great at doing? If I could get 2 or 3 volunteers, and then obviously we won't have time to go through everyone's, but if you'd like, you can submit this as one of your activities through Canvas, one of your class activities, and that's an option as well. And then I'm going to use the last minute in class to show you what I perhaps a little biasedly think is a super cool website where you can see all of the techniques I've shown you today. There's a recommender system for how and when to use them. So I want to make sure I leave a minute for that and don't keep anyone waiting. Okay, who is going to volunteer to show us their sketch?
I have a sketch, but it uses a little bit more data than that's in the table.
That's perfectly fine.
Let me
Yeah.
go ahead and cool. I'm sharing the screen. So it ends up that here's my Twitter, and just so happens that I interact with some professors, 2 of which are at the U. So I know that the departments of these guys and gal, and I thought it'd be cool if we put different departments and the relationships between them. Yes. And the weight of the edge is the number of times that they've interacted with each other, and the hue is the amount that they've tweeted. So Rami's tweeted a lot, and I've tweeted a medium amount. Pavel and Bagheera have tweeted little.
That is fantastic. So you've used a combination here of faceting and then the on node and on edge encoding.
Yeah, yeah.
So you can see that one of the reasons this works really well is, unsurprisingly, right, we're looking at some pretty small networks just to kind of get an idea of what the kind of techniques are. So you can use faceting, and you can see how intuitively when you were drawing the edges between the nodes and different facets is you gave yourself the luxury of avoiding edge crossings, right? Because you can. And you can you had enough nodes to kind of work around that. You can imagine as these networks get larger that you kind of run into that edge crossing and you lose the strength of any kind of topology encoding in lieu of really strong attribute encoding. So yeah, this looks great. Thanks for sharing. Out of curiosity, did you sketch that like on your iPad or?
Yeah,
I used, you're sharing it on your iPad. Cool.
Good notes.
Oh yeah, nice, nice, nice. Anyone else want to share their sketch before we wrap up?
I drew a picture with markers.
Okay, that sounds great. You want to hold it up to the screen? I think we can, let's see.
I'll share my screen. Oops. Actually, just kidding. I don't. How do I tell it to cancel?
Oh, no worries. I think
now
you
it's
can
sharing
just,
a screen. Now.
I think you have to go over to the stop share.
No, I don't have the stop share.
I know that always kind of gets away. I don't know if I. Oh, there you
Okay.
go. You did it.
Okay, but I just drew it with markers, and I did the Biofabric, and I realized that because there are the mentions, the quotes, and the retweets, you'd have to do multiple colors for each line, and because it's directional, you realize you'd have to do arrows on them.
Yeah, yeah.
So at first I thought it would be good, but after looking at the different colors and the directionality, I think this might be fine actually for just 5. But if you have more than 5 nodes, I think this would be ridiculous.
Yes, that is very true. And I like that you're kind of using like the idea of directionality, something we didn't look at in Biofabric, and you can kind of see there how you would use that. You can start quickly seeing the limitations of edge encodings on top of Biofabric, right? Where if you had, for example, 5 or 6 different edge types, it would just be a little rainbow there, and so interaction becomes a key part of filtering what you want to look at and versus what it is that's relevant for that.
I agree. I like it, but it would be way too much.
Yeah. Awesome. Cool. So thank you both for sharing. And like I said, if you'd like, you can submit this as an activity. And I'm going to use the last 30 seconds of lecture to show you this website. So part of our state-of-the-art report had this recommendation website. So you can find this either by going to the VDL website, or you just remember vdl.ski.edu and then MVNV. So what this has here is, it's that same topology that I kind of showed you, but you can navigate to, so if you click on a given technique, it'll take you to the summary page that will tell you, kind of summarizing what it's good for, what it's not great for, examples from actual papers, a list of papers that implement adjacency matrices, and then the summary of kind of like, where does it do well in terms of these different dimensions, the size, the type of networks, the attributes, and so forth. This is kind of a summary. So this is per visualization technique. You may also go over to the wizard and say, well, I have a network that I'm trying to look at. It's a medium network, and it's a dense network, and it has several node attributes and so forth, and kind of use this to describe your network. And that will give you this ranked list of, well, given what we know about these visualization techniques, these are the ones that we suggest that you use. And then here we highlight what were the scores for each one of the techniques as a function of size, type, and so forth and so on. So I really kind of don't want to go over. This was a super quick kind of just glimpse into something you can play around with. But if you're interested in the topics of NVNVs, then I recommend kind of going through the website, and you can see we're going to post the slides as well. And hopefully that'll give you kind of enough to go off of. And so I'll wrap up and let Alex kind of, I don't know if there's any closing remarks you want to make.
No, just
pretty much.
That's it for today. Thank you very much, Carolina. It was great as usual. And if there's any questions, we still have time to hang around for a couple of minutes.
I have a question. I know there's been some work on graph query languages, like, I don't know if it's GQL or GQL. Yeah, I'm curious if a lot of these tools leverage that. I know it's an ongoing effort for GQL. I wonder if that's perhaps the future in leveraging query languages.
So that's a good question. We do that, like we're actually building a big framework that does these kinds of matrices, multivariate network visualization, and we use ArangoDB, which uses one of those query languages. Also, the tool that I showed on Tuesday uses one of those graph databases and uses the same thing. So a lot of these network visualizations that have to deal with more than a couple of hundred nodes usually use something like that to kind of like make that more accessible.
So Neo4j, right, is what you were trying to remember, Alex?
Neo4j. Yeah.
Cool, thanks.
Yeah, because adding to that, right? Is this idea of like the underlying data and how you can quickly query and filter it to use these kind of front end visualization approaches. The data wrangling, the graph data wrangling and the graph visualization are really go hand in hand to address a lot of the limitations of trying to look at the entire graph at once. Andres, I think you were going to say something. Sorry, I cut you off there.
No, you're good. Do you ever see in the visualizations where they take kind of like an on node approach, and then you have an option to toggle the edges on and off so that you can kind of use clustering instead? Like, for example, in that instance, if you wanted to know the tweets and mentions and the quotes, you could have kind of like, you know, those inside the bubbles themselves and have them be a certain size, and then use clustering instead of the lines and toggle that on and off. Do you ever see that?
So I think what you're getting at, and correct me if I'm wrong, is this idea of taking the edges or the topology and encoding it as attributes on the nodes. Is that what you're saying?
Yeah.
So that is one of the data operations, and I think you're getting at something that's really interesting, which is what is an edge and what is a node is very fluid, right? Because the fact that you have retweeted with you retweet someone, right, is an edge that connects with that someone, but is also an attribute of the node in the sense that that person retweeted this many times, for example. And so there's a whole line of work that one of the students that used to be at the VDL group that does called orograph, which is about wrangling from one to the other. And if you once you wrangle the data, for example, to take edge information, I can't see this as it's too cluttered. I now want to see this as information on the nodes. Once you make that an attribute, then yes, you can leverage that as on-node encoding. And so you're still using the same visual techniques, but what you've done there is you've changed the underlying data to reflect a different possibility of encoding that. So does that sound like I answered kind of what you were getting at? I may have kind of maybe a little bit of a
no,
okay.
that was my question. Yeah, thanks.
Yeah, if you're interested in it, it's called orograph, graph wrangling, and there is an interface that allows you to say, hey, I now want to make this a node, and it will do that for you, and it visualizes it as a no-link diagram. So if you look up orograph in the VDL group, you can read a whole paper on it. I mean, if you're interested, and that's a whole area of research.
Cool, thanks for that.
Yep.
Okay, thanks. Then I think we can stop the recording. And yeah, thanks, Caroline, again.
Yeah, of course. Yeah, and if anyone thinks of anything else, just feel free to reach out to me. If you somehow can't find the link to something, always happy to chat about NVNs.
Thanks, bye.
Okay, bye.